This is a fun question. It says that we have a source that emits a sound with a frequency of 1,000 hertz, and it's moving 20 meters per second towards a stationary reflecting wall. If the speed of sound is 340 meters per second, the observer at rest directly behind the source observes the difference in frequency between the direct sound and the echo of what? Okay, so this is going to actually, because we're looking for a difference of frequency, it's actually going to involve us to do this twice over. So I know that, let's draw a picture first. So I have an observer. This is my observer. And I have my source. My source is a little speaker. I have a reflecting wall over here. So my source is moving at 20 meters per second towards a stationary wall. So what's going to happen is that the source is going to emit its sound waves. And some of the sound waves are going to get stacked up on the front side of this. And they're going to hit the wall and return off of the wall with the same frequency. However, since the observer is going away, it's going to emit a backwards sound wave at a larger frequency. So let me actually draw a few more of these in the blue to make it seem like that's what's happening. So our frequency that we're emitting towards the wall is going to be a higher frequency because of the Doppler shift. It's going to be pushed forward. So we're going to produce these waves closer towards each other as the source produces the sound and moves towards the wall. So the reflected sound, the echo sound, the frequency observed is going to be the velocity minus or plus the velocity of the observer divided by the velocity of the sound divided by the velocity of the source times the original frequency that we're at. And that's going to be our source frequency. So when I calculate this out, I have F naught is equal to 340 meters per second. My observer has a zero speed. So divided by 340 meters per second minus my source. And since I'm going towards the observer, right, as I go here, this path that this sound travels from the source to the observer gets shorter and shorter. So by going towards the reflecting wall, I'm actually getting closer to the observer. Seems a little weird, but the reflection on here causes us to have to travel a shorter distance. So I get a positive sign, I get the minus sign from the equation, and this value is a positive 20 meters per second. And this is all going to be times by the 1,000 hertz. So 340 divided by 320 times 1,000 hertz. And this is the echo. Well, if I go and do the same calculation again, my observer, V over V minus V source times the frequency of the source, this is going to be for the direct. So this is going to be the red sound waves that travel away from the speaker. So this is going to be 340 meters per second, 340 meters per second, minus 20 meters per second. My source is traveling away from the observer, right? I'm getting further apart. So I introduce that minus sign over there. And then again, 1,000 hertz original signal. So this is going to be 340 divided by 360 times 1,000 hertz. So we have 340 divided by 360 divided by 1,000, and this works out to be 944 hertz. The 340 divided by 320 times 1,000 is going to work out to 1,063 hertz. And if we take the subtraction of the two, we get pretty much 60 to get up to 100 or 1,000, and 60 more. So 60 is a little bit, it's around 120, 118 hertz is going to be our right answer.